Hello, everyone. We are Group 21. Our presentation topic is a scalable pipeline for graph processing and learning. So what are graphs? They are actually very important data structures and commonly used in many domains, such as social science, biology, and chemistry. Here we give several examples. The most common graph data are social networks. We are actually generating graph data on social apps every day, such as TikTok, Instagram. Besides, the molecular structures and protein interaction networks are also graph data. As you can see, graph structured data are very common in real life, and it can be very beneficial to analyze those graph structures because they usually have some inherent features. For example, nodes usually form clusters, and nodes with distinct degrees tend to behave differently. Besides, nodes with similar features are more likely or unlikely to connect to each other. More importantly, by understanding those data, we can apply them to link predictions, anomaly detections, and many other tasks. However, there do exist some great challenges in analyzing graph structured data. First, the scale of graphs can be very large and meanwhile very sparse. For example, the social network data of Twitch, a game streaming platform, has over 160,000 nodes and over 6 million edges, but the average degree for each node is only around 10 to the power of minus 5. Additionally, when modeling the graph with deep neural networks, good representations for a node are needed to encode useful information, and such graph neural network is usually difficult to train. We also need to think about how to build a single efficient pipeline from the raw data processing to modeling prediction. We need to speed up the whole process so that GNN can be applied in real practice. Therefore, our goal for this project is to design and implement an end-to-end processing and learning pipeline for large-scale graphs. In this presentation, we will first introduce our data processing pipeline and then our implementation of graph neural networks. First of all, let me introduce our dataset. We use a Twitch gamer dataset, which are Twitch social networks of gamers who stream in different languages. Nodes are the users themselves, and the ages are mutual friendships between them. Vertex features are extracted based on the games played and elect locations and streaming habits. More specifically, we have two CSV files. One records the features of every user, and the other records the friendship between two users. The Twitch gamer dataset is actually overwhelmingly large. As mentioned before, it includes over 160,000 nodes and 6 million ages. We need to figure out an efficient way to handle this data without memory issue. So we first use MongoDB to store all the data, where the node ID is the key and the features of the ages are values. We then employ SparseSQL to enable fast query processing. We need to convert ages into an n-by-n matrix. Each row is a one-hot vector that records the friendship with other users. N is the number of total users. Simply reading CSV file into a NumPy array will cause severe memory issue, since the size of matrix is too large. To avoid out-of-memory issue, we directly record the non-zero values in ages and convert them into a compressed sparse row rather than a NumPy array. This can effectively reduce memory consumption. We will then feed our processed data to our graph neural network. Okay, next, let me pass the time to James. He will introduce our implementation of graph neural networks.
After processing the large-scale graph, we can apply machine learning algorithms on the processed data to make useful predictions. Now I will introduce the use of graph neural networks, or GNNs, in our pipeline. On the left side, imagine this is a toy example of two subgraphs of the Twitch network. One task we are interested in is to predict whether a user is and underage. Suppose the yellow indicates the underage and the red indicates the mature users. Given A and B is connected to C, what feature will C be? And given D and E, whether F is mature or immature. A reasonable guess would be C is underage and F is mature. In social networks, this is a famous quality called homophily, which says that nodes with similar attributes are more likely to be connected. Therefore, to learn a good representation for a node, we are interested in the information in the neighboring nodes as well as the node itself. There has been a proposed method called Graph Convolutional Network, or GCN, as you can see on the right side. It is one of the earliest proposed GNNs. It passes information from the neighboring nodes to the target node and aggregates the information from the neighborhood to generate a representation of the node. This is similar to the convolutional layer in computer vision. Such a node representation is then used for downstream predictions. The previous method, GCN, is extremely powerful in encoding graph structures. However, it is also computationally expensive, especially when a node has a large degree. It needs to aggregate information from a lot of neighboring nodes. Here are two optimizations we did to speed up the learning. First, we use a GPU device to process learning for each node in parallel. Second, instead of going through all the nodes in the neighborhood of a given node, we downsample only a small subset of neighbors for the information aggregation. This idea is proposed in the more recent works, such as GraphSage and GraphSaint. We have pasted the citation below, so if you're interested, feel free to check out. Let's see the performance for predicting the maturity of the Twitch users. We experiment the learning algorithm, GraphSaint, on both GPU and CPU. As we can see, GraphSaint can outperform the logistic regression baseline significantly. Running the algorithm on the GPU can be almost 3 times faster than on CPU. In conclusion, given that the network data in real world can be very large scale, we build a scalable pipeline to process the data. We leverage MongoDB, a scalable storage system to store key value pairs, and Sparse SQL, an efficient data processing framework to generate a sparse matrix representation to replace the full node adjacency matrix. To learn the complex graph structures and extract useful information from the neighborhood, we use the more powerful graph neural networks, and we optimize the network with the recently proposed sampling approaches.